In this video, we're going to talk about Experiment 5, which is metathesis reactions and net ionic equations. In the previous video that focused on Experiment 4, we looked at redox reactions, and we got to start with using our ability to make observations to determine if a reaction occurs and to determine what the products are based on the physical characteristics and the chemical characteristics of the reactants and the products. In Experiment 5, we're going to do the same thing. The only difference is that we're going to be focusing on metathesis reactions. So let's kind of get a start by just generally talking about what a metathesis reaction is and how do we categorize them. So one of the more important questions of this is, what makes metathesis reactions take place? What drives a metathesis reaction forward? And the unifying thing behind all of metathesis reactions, what makes them take place, is that we're removing ions from solution. That's what drives the metathesis reaction to take place. So in that sort of concept of removing ions from a reaction, we can then categorize how the ions are removed to categorize the different metathesis reactions. Now, in the image that I show here, this is a classic type of metathesis reaction where we do a precipitation. So in this case, we're combining lead nitrate with a solution of sodium iodide, and what's precipitating here is this nice yellow solid is lead iodide. So in one broad category, we have what we call precipitation reactions, and the unifying theme of precipitation reactions is that we put two ions together that form an insoluble salt, and they precipitate out of solution, essentially removing the ions as a solid material which can be separated from the liquid. Now there's another category of metathesis reactions that involves the formation of a weak electrolyte, and these are broadly known as acid-base reactions. So the classic weak electrolyte that's formed is water. When you combine hydrochloric acid and sodium hydroxide, they make water, which is a weak electrolyte. Water is not a strong acid or a strong base, so it doesn't completely ionize, and therefore we're taking two ionic compounds and we're forming something that's a weak electrolyte. And the same can be said for the formation of a weak acid or a weak base. Because we're forming a weak acid or a weak base, it doesn't completely ionize, and therefore we removed ions from solution. And then the last category is what we call gas-forming reactions. In gas-forming reactions, ions come together to make a gas. And then the gas bubbles out of solution, allowing the ions to leave the solution. So we have precipitation reactions, we have acid-base reactions, and we have gas-forming reactions. Now, how could these reactions be useful in everyday life? Well, here's a classic example, this image right here. One thing that's really important with precipitation reactions is trying to identify if you have something in solution. So if you want to know, do I have lead in solution, by combining the unknown with some iodide will result in the precipitation of lead iodide, which has this yellow color. And then you can detect whether there's a toxic element in that solution or not. So this kind of goes back to our experiment where we did qualitative analysis. And in our qualitative analysis experiment, we do several examples of metathesis reactions. We're going to see those here: the reaction of carbonate with acids, the reaction of ammonium chloride with bases. All of those reactions that were used in qualitative analysis were metathesis. Many of those reactions were metathesis reactions. So now the other part of this experiment is sort of getting some practice with writing molecular, net ionic, and writing molecular equations, complete ionic, and net ionic equations. So that's what we're going to kind of start to tackle here, and we're going to talk about how we can write these things. So there's a couple of steps that we can follow when we're doing this. So for example, we have just like we would in the upcoming videos where we're going to actually look at these reactions, we have a solution of aqueous lead nitrate and we're reacting it with aqueous ammonium bromide. So we want to be able to predict the products and determine what the molecular, complete, and net ionic equations are. So the first thing we have to do is we have to write the reactants. So we're given these two reactants, lead nitrate and ammonium bromide, and we have to be able to get them down on a piece of paper. We have to be able to write them. So this goes back to nomenclature. So we're going to be practicing nomenclature. So now lead we know that lead is Pb from the periodic table. We also should have memorized that lead has a +2 charge. That's how we know that when we write lead nitrate, we put PbNO3. Now, NO3 is an example of a polyatomic ion, which we have to memorize from the table in the book, in the textbook from lecture. So we know that when we write our NO3, which is the nitrate, we have to put 2 down here because the NO3 has a -1 charge, whereas the lead has a 2+ charge. So this is just a review of nomenclature. I'm not going to go into too much more detail other than to say, if you have difficulty writing these things, practice your nomenclature from the textbook. And then the same thing goes with ammonium bromide. So with ammonium bromide, we have the ammonium ion, NH4+, and we have the bromide anion, which is Br-. So when we put them together, we get NH4Br. And these are both in aqueous solution. So that's the first step. You have to write your reactants. Now the second step with metathesis reactions, and you learned this in lecture, is we have to exchange the ion partners. So we know that these are soluble because the prompt tells us that they're both aqueous. The question is when we put these things together, do any of the cation and anion pairs come together to form something that's not soluble, or something that reacts as either an acid-base reaction or a gas-forming reaction? So now to do that, to exchange the partners, we have to use the charges of the ions to write the products with charge balance. So let's take a look at what I mean. So on the other side, we're going to take the lead, which is our cation 1, and our bromide, which is our anion 2 from the second compound, and we're going to put them together. And because lead has a 2+ charge and bromide has a -1 charge, we're going to get PbBr2. And then if we take our anion from the first compound and our cation from the second compound and put them together, we get ammonium nitrate, and that's going to be a 1-to-1 ratio of these polyatomic ions because ammonium has +1 and nitrate has -1. So now that we've written our products with proper charge balance, we just have to balance the entire equation. So to make it balance, I have to add a 2 here to account for the fact that we need to have 2 bromides to go with the lead. So we have to add a 2 for these, the ammonium bromide, and a 2 for the ammonium nitrate. Now that again goes back to chapter 2 in terms of balancing reactions. Now the third step is where metathesis reactions come in. So now we have to decide, is a reaction really taking place? And the first step for doing that is to determine the phase labels for the products. So we have to know our solubility rules. We have to know whether something is a strong acid or a strong base. And we have to know whether something forms a gas. So we're going to use these 3 tables to determine what the phase labels for our products are going to be. And that's going to be our first step to determine whether a reaction took place. So in this case, we know that lead bromide, most compounds of lead, especially those with the halogen anions, are going to be insoluble. So we're going to put a solid here for this because according to the solubility rules, this is not soluble. And then ammonium nitrates, almost all nitrates are soluble, so we put aqueous for the nitrate. And now we have to decide if a reaction took place. So a reaction takes place if ions are removed from the solution. So do we form a precipitate, a weak electrolyte, or a gas? And in this case, we form a precipitate. So yes, a reaction has taken place, and that is because we formed lead bromide as a solid precipitate product.
Okay, so let's look at this reaction of copper chloride with sodium hydroxide. So if we exchange the partners, we're going to take the copper and we're going to put it with the hydroxide. Now remember, copper is copper 2+, so I'm going to put a little 2+ here just so that I remember. So that means that the hydroxide is -1, the sodium is +1, we memorize that, and the chloride is -1. So that's just going to help me kind of remember what my charges are as I go along. So with the copper, when I write the copper hydroxide, I have to put copper OH2 in order to balance it. And then I'm also going to put, I'm going to exchange my sodium and chloride, my anion and cation from the other one. So I'm going to get sodium chloride. Now, the next thing I have to do is think about phase labels. So let's tackle the easy one. Sodium chloride, most chlorides are soluble. Sodium chloride is definitely soluble. And copper hydroxide in this case is going to be a solid. Most hydroxides, including copper, are insoluble, so we get copper hydroxide solid. Now, we have to balance this. So I have two hydroxides on the right, so I'm going to have to put a 2 for the NaOH and a 2 for the NaCl to get it balanced. So does this one give a reaction? The answer is yes. Now let's look at the next one. So we have iron nitrate, aqueous, and we have sodium sulfate, aqueous. And now we're going to write our product. So we're going to do our exchange. So we're going to have FeSO4, and we're going to have sodium nitrate, NaNO3. And we're going to work on our phase labels. So this is going to be aqueous, for sure. Most nitrates are soluble. Now here's the one where you might be tempted to immediately say, well, the iron sulfate has got to be a solid. If you look at your solubility rules, iron sulfate is actually soluble. So in this case, we're also going to put aqueous. So this was a bit of a trick, this one. So in this case, because we start with aqueous products and we end with aqueous products, all the same ions in solution, basically they're all spectator ions, this one is going to be a no reaction. So that's how you would go about doing precipitation reactions. Let's take a look at the weak electrolytes. Okay, so the barium hydroxide, aqueous, plus the hydrobromic acid, aqueous. Okay, so we're going to exchange partners. Now in this case, what we have is we have an OH minus and an H plus. That's going to give us the weak electrolyte H2O. And we're going to put liquid there for that phase because H2O is not a strong electrolyte, so it gets the little L for liquid. Okay, so let's look at this reaction of copper chloride with sodium hydroxide. So if we exchange the partners, we're going to take the copper and we're going to put it with the hydroxide. Now remember, copper is copper 2 plus, so I'm going to put a little 2 plus here just so that I remember. So that means that the hydroxide is -1, the sodium is +1, we memorize that, and the chloride is -1. So that's just going to help me kind of remember what my charges are as I go along. So with the copper, when I write the copper hydroxide, I have to put copper OH2 in order to balance it. And then I'm also going to put, I'm going to exchange my sodium and chloride, my anion and cation from the other one. So I'm going to get sodium chloride. Now, the next thing I have to do is think about phase labels. So let's tackle the easy one. Sodium chloride, most chlorides are soluble. Sodium chloride is definitely soluble. And copper hydroxide in this case is going to be a solid. Most hydroxides, including copper, are insoluble, so we get copper hydroxide solid. Now, we have to balance this. So I have two hydroxides on the right, so I'm going to have to put a 2 for the NaOH and a 2 for the NaCl to get it balanced. So does this one give a reaction? The answer is yes. Now let's look at the next one. So we have iron nitrate, aqueous, and we have sodium sulfate, aqueous. And now we're going to write our product. So we're going to do our exchange. So we're going to have FeSO4, and we're going to have sodium nitrate, NaNO3. And we're going to work on our phase labels. So this is going to be aqueous, for sure. Most nitrates are soluble. Now here's the one where you might be tempted to immediately say, well, the iron sulfate has got to be a solid. If you look at your solubility rules, iron sulfate is actually soluble. So in this case, we're also going to put aqueous. So this was a bit of a trick, this one. So in this case, because we start with aqueous products and we end with aqueous products, all the same ions in solution, basically they're all spectator ions, this one is going to be a no reaction. So that's how you would go about doing precipitation reactions.
Okay. And then also what we're going to do is we're going to take a look at acid-base reactions. So in acid-base reactions, these can either form a weak electrolyte, ions are removed as weak electrolytes, and the main ones are either water or another weak acid or base. So H2O is a weak electrolyte, or things like acetic acid, nitrous acid, any acid that's not a strong acid would be a weak electrolyte. So as I said, weak electrolytes are anything that is not a strong acid or a base as defined in table 5.2. So take a look at the following and decide, will they give you a reaction? So pause the video and over here, see if you can determine whether these will form a reaction, whether these will give a reaction or not. And then we'll go over it.
Let's take a look at the weak electrolytes. Okay, so the barium hydroxide aqueous plus the hydrobromic acid aqueous. Okay, so we're going to exchange partners. Now in this case, what we have is we have an OH minus and an H plus. That's going to give us the weak electrolyte H2O. And we're going to put liquid there for that phase because H2O is not a strong electrolyte, so it gets the little L for liquid. And then that's going to give us barium bromide, which is soluble, as our other product. So to balance everything out, we need 2 HBr, and that should get us all balanced because we have the H2, we have the O, and so the other thing we have to do is we got to put 2 for the H2O. And then that should get us balanced. Okay, so does a reaction occur? Yes, a reaction occurs because we're forming the weak electrolyte H2O liquid. So that's going to be a yes for that one. Now let's look at the next one. We have sodium acetate, C2H3O2 aqueous, plus we have HCl aqueous. So if we do our partner exchange, we're going to get acetic acid HC2H3O2 plus we're going to get sodium chloride, and that's going to be aqueous. Now let's talk about the HC2H3O2. This is acetic acid. And if we look at our table of acids, we're going to see that acetic acid is not a strong acid. So this is going to get an aqueous because it's dissolved, but it doesn't break up. So if we were to write the net ionic here, that's a good thing to do, is to write the net ionic. What we're going to have, so we should write the net ionic, but the question with the net ionic is, do we have an actual reaction taking place or no? And the answer to that question is yes, because here's why. Since this is a weak electrolyte, we have C2H3O2 minus aqueous, plus we have H plus aqueous. The Na and the Cl go away. Those are spectators because they're on the other side. When these come together, this makes HC2H3O2 aqueous. And this doesn't break up in solution. This stays together because it's a weak electrolyte. So yes, we are having a reaction, and the reaction is that we're forming the weak electrolyte acetic acid. So don't be confused by the fact that the water is not the only weak electrolyte. There are other weak electrolytes which include weak acids and weak bases. So if you form a weak acid or a weak base, those will not break up in the net ionic. They'll stay together, and then you'll have a reaction.
Now the last class of acid-base reactions are the gas-forming reactions. So in this case, ions are removed as gases. And the following ions and their derivatives produce gases. So we have carbonates, sulfites, sulfides, and ammonium. So the reaction of carbonate and sulfite. So the intermediates, H2CO3 and H2SO3, are unstable and decompose to water and carbon dioxide for H2CO3, or for H2SO3, they form SO2 gas. So whenever you add an acid to CO3 2 minus or to carbonate or sulfite, you're going to get either carbon dioxide or sulfur dioxide gas. So for carbonate, 2HCl plus sodium carbonate gives the intermediate product, H2CO3, which spontaneously breaks down into water and carbon dioxide gas. And then in addition, for both of these compounds, you can have another form of this compound where you can have hydrogen carbonate or hydrogen sulfite. And that puts that here. So this would be the bicarbonate, for example. And again, when you add HCl, this is going to form CO2 and water. The only difference between these two is that this requires 2 equivalents of HCl to form CO2, whereas this one, because it has an H already, only requires 1 equivalent. So the reactions of sulfide. Sulfide, S2-, when you react this with acid, you make H2S, and H2S forms a gas, and it has a rotten egg odor. So again, when you mix HCl with sodium sulfide or hydrochloric acid with sodium hydrogen sulfide, both of these reactions will lead to dihydrogen sulfide gas. And then we saw in experiment 3 the reactions of ammonium. If ammonium ion is present and you add a base, it will form ammonia gas. So ammonium chloride plus sodium hydroxide deprotonates the ammonium ion, making water, and then leaving behind the NH3, which comes out as a gas. And you can actually detect this with wet litmus paper. So in each of these experiments, the way that you would do this in lab is you would take the 2 reactions that are listed. So there's going to be 2 reactions, just like we had before. We had the lead nitrate and the sodium bromide. And you're going to put 10 to 15 drops of the 2 in a test tube. And then you're going to gently mix. Then you're going to be detailed in your observations. So you want to note colors of the precipitate, color of the solution. You want to note if a gas is formed, and if it is, what is the color and the odor. Then you're going to decide, based on your solubility rules, strong acid, strong base table, and gas forming reactions, you're going to write about a reaction, balance it, and use proper phase labels. And that's how we're going to decide what the phase labels would be. And then we would just discard the contents of the test tube and start the next one. Now, for reaction 13, and we're going to look at this one in a minute, we would normally perform this one in a hood because it produces a toxic gas with a rotten egg odor. So let's talk a little bit about safety for this experiment. We're going to be using acids like hydrochloric acid and sulfuric acid, and also bases like sodium hydroxide. These are corrosive, so we must wear safety glasses and lab coats. We must clean up spills immediately, and you must wash your skin if you ever get an acid or a base on it so that you don't get burned. In some cases, we're going to be forming gases that are toxic. In this case, the gas is not necessarily toxic, but it's more very unpleasant in its odor. You'll stink up the whole lab. So we perform 13 in the hood because we want to make sure that it doesn't make the whole room smell. And then we have to get rid of waste safely. So we place all of our waste in a waste beaker, which the lab techs will take care of. And then you just want to use the minimal amount of water to wash. And it's always important to keep the reagent bottles capped. This has led to a lot of lost cell phones over the years. So make sure that when you're doing these types of reactions, you keep your cell phone off the bench. In this part of the video, we're going to look at the actual reactions that we would do in lab, and we're going to make our observations. So if you take a look at the textbook, each reaction has its own set of lines, and you'll see that the reaction numbers correspond to what's in the textbook. So reaction 1 is the mixing copper 2 sulfate with sodium carbonate. So what you're going to want to do is, as we're going through the videos, you're going to want to write down your observations. You're going to want to note things like the color of the precipitate, the color of the supernatant. We'll talk a little bit about that in a second. Whether a solid is formed, what the color of the solid is, if a gas is formed, what is the color and the odor of the gas, so on and so forth. So be very detailed in your observations as we go through the videos. Now, let's take a look at the first one. And the reactions of copper are really interesting because we know from experiment 4, where we did the redox reactions, that copper 2+, which is what the copper we're using here is, copper 2+ has a blue color. And that's just going to allow us to track whether the copper is in the supernatant or in the precipitate. Now, when we run these reactions, when we're done, what we normally do is we take them and we put them in what we call a centrifuge. and the centrifuge spins the samples and increases the relative gravity on the solution. And what that does is that separates the solid part from the liquid part. And we call the solid the precipitate, and we call the liquid the supernatant, which is above the solid. And in cases where we make solids, I will tell you what the colors of the supernatant are and what the colors of the precipitate would be. Now, because copper 2+ is blue, we should be able to figure out whether the copper is in the solution or in the solid, depending on what of those two things are colored. So let's take a look. So now, what we're doing in this video is we have the copper sulfate in this solution down below, and we have the sodium carbonate up here in this pipette. And we're going to add the sodium carbonate into the calcium sulfate. So what you can see is that a solid formed, and whenever we form a solid, we're going to take that solid and we're going to centrifuge it. And when we do the centrifuging, that's going to allow us to see what color the solid is and what color the supernatant is. So in this case, when we centrifuge this product, we are going to see a blue solid at the bottom, a blue colored solid at the bottom, and a transparent or colorless supernatant. Now let's look at the reaction of copper sulfate and barium chloride. So what we have here is we have the copper sulfate, again it's blue, so we see that, and in this we have the barium sulfate. And you can see that when we run this reaction, we get a solid. And if we were to take a little bit of this and this mixture and spin it down in a centrifuge, we would get a white precipitate and a blue-colored supernatant or solution above the precipitate. So now let's look at copper sulfate and sodium phosphate. So in this video, we're going to take the copper sulfate, which is up here in the pipette, and our sodium phosphate, which is down here in the solution, and we're going to add them together. And what you can see is that the solid that forms has a blue color, and the supernatant that is there, the solution phase, has a transparent color. Okay, so now in this video, we're going to take a look at sulfuric acid and hydrochloric acid reacting with sodium carbonate. So this is a relatively long video where they look at a variety of different carbonates with different acids, but in this video, in this part of the video that we're going to look at, this is going to have sulfuric acid on the left and hydrochloric acid on the right. And the observations are basically going to be the same. It's just that in one case, the reaction is going to take place a little bit faster. The one on the right is going to take place a little bit faster because hydrochloric acid has a little bit more water in it. So what we're going to observe is what happens when we add the solid sodium carbonate into sulfuric acid and hydrochloric acid. Okay. So what we see, to kind of help you out, because this one is a little bit more challenging, if you take a look on the left, that's pretty representative of what you're going to get. So we get a formation of a gas, which has no color, or you can't see it. And you can see the same thing here. You can kind of see the gas bubbles forming. And if you were to waft this gas, it would be odorless. So that should tell you a little bit about what the gas is. And remember, we're using carbonate here with an acid. So that may help you to direct you in the right direction for what type of gas forming reaction this would be. Okay, so now let's take a look at the next set of reactions. So in this next one, we have cadmium chloride and we have sodium sulfide. So the cadmium chloride is going to be in the pipette and the sodium sulfide is going to be in the test tube. And you can see that the sodium sulfide has a slight clear, transparent color. It's a little bit yellowish, and that's the sulfide anion that has that color. So let's take a look and see what happens when we add the cadmium chloride. Okay. So if you were to centrifuge that down, so this is the solution, and separate the solid that formed from the supernatant, you would have a slightly off-white supernatant, off-transparent supernatant, the color of the sulfide, and a nice orange precipitate down at the bottom. Okay, now let's look at cadmium chloride and sodium hydroxide. Okay, so in this reaction setup, we have the cadmium chloride in solution. It's a nice colorless solution. And we have the sodium hydroxide, which is also a colorless solution. And we're going to add them together. We're going to add the sodium hydroxide into the cadmium chloride. Okay. And if you were to centrifuge that down, this mixture right here down, you would get a white precipitate and a clear, colorless supernatant. Okay, now let's look at nickel. So the reaction of nickel is interesting because nickel is like copper in the fact that it's colored. So if you look at nickel chloride, that's right over here. The nickel chloride is a green solution. And we can use that green coloration, that comes from the nickel 2+ ion, to determine what happens to the nickel, whether it's in the supernatant or in the precipitate. So it turns out that the observations for these reactions are pretty much the same, with one exception. At the end, when you centrifuge it down, there's going to be a difference, and I'll tell you what that difference is. But we're just going to look at the reaction of nickel with carbonate as an example. And you can write the same overall observations, but just note that the distinction that I'm going to make about the color of the supernatant and the color of the precipitate. Okay, so let's take a look at this video where we do, so in this test tube we have sodium carbonate, and we're going to add the nickel chloride to it. So this one is reaction 9. Okay. So now, for reaction 9, if you were to centrifuge that down, what you would get from reaction 9 is a slightly greenish colored, or a slightly colored precipitate. It'd be close to white, but have a little greenish tinge to it down at the bottom, and the supernatant would be colorless. Now, let's talk about what happens with the nickel chloride and the silver nitrate. So reaction number 8, when you add the silver nitrate into the nickel chloride, or vice versa, you would get something that looks very much the same. However, with reaction number 8, when you centrifuge that down, what you would have is a white precipitate at the bottom, and the supernatant would have a slightly greenish color. Okay, so that should tell you about where the nickel is in those two precipitates. And there's going to be a similar thing for reaction 10 and 12. Again, these reactions, not all of them have very, very different observations. So it turns out that reaction 10 and reaction 12 look very similar. And in this case, it's going to look almost like nothing happened in the reaction mixture. There's not going to be much in the way of observations, with a couple of exceptions, and I will go into that after we watch the video. So this is the combination, what you're going to watch in the video is the combination of hydrochloric acid and sodium hydroxide. And then we'll talk about hydrochloric acid and sodium acetate as well. Okay. So you can see that that was the results of the mixing the two colorless solutions together. Now with the hydrochloric acid, so with reaction 10, you're going to want to note that if you were to feel that beaker, it would feel a little warm. So that may be an indication that something happened. And something also happens with reaction 12. When you combine hydrochloric acid and sodium acetate, it looks exactly like what just happened. The only difference is with the sodium acetate, you get a little bit of a vinegar odor. Now remember, vinegar is acetic acid. So that may also help you to determine what happens with the sodium acetate and hydrochloric acid. So now let's look at the reaction number 11. So reaction number 11 is in between 10 and 12 that we just looked at. And this is the reaction of ammonium chloride and sodium hydroxide. Now we actually already saw this reaction back in experiment 3 when we were doing qualitative analysis. So what they have down here is they have the ammonium chloride, that's a solid, and they're going to add the sodium hydroxide to it. And then they're going to heat it a little bit, but you don't really have to heat it. The reaction is going to would produce the same effect without heating it. So they're going to heat it until it boils, but you don't have to do that. So you don't have to, this gas forming that's happening here, this is just them heating it. But here's how we know that a gas is formed. When you put wet red litmus paper over it, it turns blue. And that should tell you something about the reaction that's taking place and the fact that we did form a gas. So this is ammonium chloride with sodium hydroxide. Now, let's take a look at hydrochloric acid and sodium sulfide. So sodium sulfide is down here in the as a solid, and they're going to add a little bit of hydrochloric acid to it. Now, so that's basically the observations that you would see in lab. Now remember, this is the one that we said that you need to do in the hood. And the reason for that is because if you were to do this out on the bench and you were to waft this, you wouldn't even have to waft it, you would just smell it. You would get a very, very strong odor of rotten eggs. So definitely some form of a gas is coming off of this, and that gas has a strong rotten egg odor. Okay, so for reaction 14, it turns out that we tried to take a video of reaction 14, and the reaction it gets so dark so fast that it's hard to see. So we just opted to go with a photograph so you could see the color of the supernatant and the color of the precipitate. So this is the combination of lead nitrate with sodium sulfide. And the sodium sulfide again has this sort of yellowish color that's consistent with the sulfide. And the lead nitrate is a clear colorless solution. And when you add in the sodium sulfide into the lead nitrate, you get this blackish brown precipitate that forms very rapidly, and it basically blacks out the whole solution. If you were to centrifuge this down, this black precipitate would be at the bottom, and you would have this colorless transparent solution at the top. Okay, so let's look at lead nitrate with sulfuric acid. So here we have our lead nitrate, and we're adding the sulfuric acid in, and you can see what happened. Now, if you were to take this and centrifuge it down, you would get a white precipitate and a transparent supernatant. Okay, now for the last one, this is the mixture of potassium chloride with sodium nitrate. So he's taking a little bit of potassium chloride and he's going to put it in this test tube. And this is the sodium nitrate. He's going to put a little bit into that test tube, and then he's going to pour the potassium chloride into the sodium nitrate. And you can see that it's the two clear colorless solutions have given a clear colorless solution. Okay, so you have to decide whether some kind of reaction took place there or not. So for this experiment, you're going to want to write down all those observations. You're going to want to make notes in your. You're going to want to make sure that you write down the complete net. I'm sorry. You're going to want to write down the molecular equation, the complete ionic, and the net ionic equations on the various lines in the textbook, and then you're going to submit the whole thing on the day that the lab is due according to the syllabus. Now make sure that every reaction is balanced, meaning that the ionic compounds have the correct charge balance, and that the overall equation has the correct is correctly balanced, and that the phase labels are correct, and that everything has a phase label, because that's what we're going to be grading you on. So those are the important things for this. And then when you're done, make sure it's neat and legible. You can upload it to Blackboard for grading. If you have any questions, you can ask your section instructors. Good luck, and I hope that this was helpful in letting you see some metathesis reactions.